So we've already seen a couple common steps as far as having to deal with strings, tidying those up, looking at the types of data and maybe doing some conversion. Some other common steps that might come up would be dealing with missing values, making sure that the missing values are appropriately represented. Sometimes things might be mislabeled in your data. You might often come across dates, and so being able to deal with date type of objects is a common skill we'll need. Also, when dealing with sports data, you'll get team names, athlete names, and if they are coming, especially from different sources, you'll find that there may be inconsistencies or things may be misspelled. So that's another common thing that we'll have to be aware of that we could come across and be able to deal with. So all of this can be done with a few packages in R. One of those is a dplyr. We already saw an example of this one. So just to say a bit more about dplyr, it's basically a grammar for data manipulation, another Hadley Wickham creation, and it provides most of the things that we'll need just for manipulating data, doing summarize, aggregation, filtering, subsetting, all of these kinds of things would happen with the dplyr. If you haven't already used it or installed it, you can do it through these DevTools commands to get the most up-to-date version. Some of the basic things that we'll use in dplyr will be selecting, filtering. These are both ways of subsetting our data. So select would be when we're subsetting by column, and filter would be when we're subsetting by row. Mutate was the example we saw before, and that's really just any kind of transformation you want to do to a variable where you're not actually changing the length of the vector. You're retaining the length, but maybe you're doing some kind of operation, numeric operation to it, or converting it into a factor, or things like this. Summarize would be when we're going from many values to a single value. So any kind of aggregation would be done through the summarize function. And then the group by is just, we can perform any of these operations by a categorical variable or a set of categorical variables, and that would happen through a group by command. And then that piping operator, actually, we've already seen when using the rvest package, and it's just a way to string together kind of a chain of commands easily without having to do any kind of messy nesting. That's very difficult to read. So it's just a kind of convenience function. And then we have tidier. And tidier is really all about reshaping our data. So when you want to go in between wide and long format, that would happen with the tidier package. So there's kind of fewer commands that I think you really need from this one. The main workhorse ones are going to be the gather and the spread command. So the gather is going to be used whenever we want to go from a wide to a long format. So it's bringing together multiple columns into sort of a single stacked structure. And then the spread does the opposite. So it breaks down sort of a key value type of pair long structure into an array of columns. And then the separate commands actually, in the case where you might have a single vector that you're wanting to break up into multiple, you could do that with separate. So let's see examples of these things in action. And I wanted to kind of give a more realistic type of example in terms of like where your goal is to actually measure something of interest. So let's say that we're looking back at performance outcomes at the Australian Open, one of the 4 major Grand Slams in tennis, the 4 most important tournaments of the year. So let's say we have multiple years of the Australian Open, and we're interested in knowing like who had the most surprising result, right? So maybe a series of upsets. How would we measure that, and who would come out on top? So this actually is an example of one player that we might expect to be in that group. This is Denis Istomin, who was ranked outside of 100 when he played Novak Djokovic this year at the AO, but actually won that match, so that was a pretty major result. So that might be something that we would characterize as a surprise, and no one thought he would be able to win that match, and he did. So first, we already saw an example of how we could get Australian Open results from this tennis UK site. And so if I want, let's say, several years, so I'm interested in the 2015 to 2017, and this is an example where looking at that pattern structure that we saw before would be particularly useful, because I need to go across multiple files now to get all of that data in one place. So we saw before the URL, I could represent it as this pattern. So I'm only interested in the AO, which makes it a bit more straightforward. The only real thing that's going to change to get multiple years of data would be the year element. So I've basically abstracted the URL into this pattern. So given that pattern, how do you think you would go about collecting these 3 years of data into a single data frame? Does anyone have an idea how they might tackle that one? That would be like an apply command? Yeah. So there are a number of ways to do it. So this is one using one of the, or a combination of the apply type of commands. So here's one way that you could do it, and I'll just actually run this in the console. So first we have our URL pattern. So this isn't actually the URL I'm going to give, but it sets me up for all of the URLs for the 3 years. So after I've run that, now what I've done in this step is with the sapply and the substitution command, I can replace year in this string with the particular year that is at that stage of the apply. So it'll run through all of the years, and then it will do this replace through this kind of anonymous function that I'm using right here. So in the end, I get the 3 URLs for the different years. And now I'm ready to do an apply and rbind on those to get a full data structure. So let me break down exactly what's happening here. So the first bit is this lapply command will take each URL and apply the read CSV. And so we know the read CSV is going to return a data frame for that particular URL. And then what lapply is doing is collecting that into a list. So this will return a list of 3 elements. Each one will be a data frame. And they all, for these years, have the same structure. So I can use a do call rbind to actually go over all of those elements in the list and stack them into a single data frame. And then, we can look at the contents of the data frame. We had seen an example before. We have information about the event, and then each row is a match result. The only difference here is now we have multiple years. So this is a fairly straightforward way of doing that one. Okay. So once we have this data, we need to do some checks on it, right? Because it's just come from the web. We don't necessarily want to trust it right away. So one of the things that we'll have to do is kind of inspect the individual variable, get familiar with what variables in there, what data, how they should be represented, and if there are any issues that need to be addressed. So I think the first thing that you should often do is look at the classes. This can be done, now that structure command will actually go ahead and tell you that first, the information here is actually telling you about the class for that particular variable. And then you could also do that, for example, with the commands like this. So that will run through, what it's doing is running through the rows, or running by column, because I've indicated 2, so that will go by column, and it'll apply the class to every variable. And then I've just tabled it to give an overall summary. So in this case, the result would say that there's all characters, which would be something that might be a tip-off if that were what you saw, because you know that there probably should be numeric values as well. I think another thing that's useful when doing any variable inspection is to use a kind of staged way of looking through the values. So sometimes if you just do like a struct or a summary, there could be some issues that are hidden in that. I mean, sometimes it'll pick up big things like an extreme value, but if your data is a character and it should really be numeric, then a lot of those functions are no longer useful to you because they kind of are set up to give an appropriate summary based on the data type. So if it isn't in the data type it should be, then sometimes the standard summaries won't be that useful. So one thing that I like to do is to use a kind of stage inspection where I actually just report all of the unique values with a particular variable one at a time. So I just see everything in that, and then I can scan through them. And the way that I stage it is by using this ask command from the gtools package. And what that will do is it'll go through the loop one variable at a time, and it won't go on to the next until I press return. So, you know, it's a bit of effort, right? But, you know, it's something that, in this case, let's see. Okay, so we'll see, here's an example. I've started to go through this set, and you'll see the first few, they only have a single value, because these are things that are basically, when you're within the same event or the same tour, they don't change. So the Australian Open, for the years we're looking at, has always been at Melbourne. So not too interesting for some of these. Now we get into a date type of variable. Again, characteristics of the event, the court, the surface, those all say the same. Round, I mean, this could be more interesting because this might be something where, you know, I might want to order this or assign a numeric value if I want to do any kind of, you know, reordering of the matches based off of the round. So by default, as a character, right, these are, if they're ever treated as a factor and a factor type operation, if I haven't specifically created it, they'll just be ordered alphabetically, which would not actually be true to, in this case, to their true order. So that would be something that I would want to potentially change. Okay, and here's a very good one. So now when we get into the player name variables, this would be an area where potentially there are some issues. You could end up with like special characters here. You could have multiple names for the same player. And you can already see that the convention used with some of the names isn't always the same. Like you get some players that have, you know, 2 letters for their first name shorthand, their first name abbreviation. Some players they have hyphenation in the last name. Potentially that could be a problem if you do any manipulation on the player names or make any assumptions. So that would be something to be aware of. So anyway, I would step through these and basically just, you know, look over the values and make notes of any potential issues that I see, or if I think, oh, I need to do some more inspection with that particular variable because of the nature of the data type that it is. I think it's the best way. It takes a little bit of time, but you just need to do it, you know, the one time for that particular type of data that you're looking at. Okay, so when we look over this data, we see that it has information about, as we scan through, we see it has information about the results of the match. As we get toward the end, we find that in addition to the scoreline info, all the W and L refer to the set results. This one's actually important, I think, in this case, when we're looking at, let's say that we're going to be summarizing sort of what a player has done in a particular event. This comment column we see, it has information about completed and retired. So there are matches that have ended in retirement that are included in here, and that might be something where we might want to treat those separately from matches that completed. You know, so if a player's opponent has retired, it may be a kind of match that doesn't really reflect their own skill. So that might be something that would be important to remove or use for filtering. In the next section of the variables, we see these kind of strangely named variables. So essentially what these are different types of prices or odds that went out by different bookmakers. We get 2 pairs for each type. So there's the the bet 365, and so the winner's price and the loser's price. And this odds information is something that we could use when developing this surprise score. So remember, all of this is the purpose of using these data to try to say something about how surprising a result is in a given year. If we wanted to summarize the surprise, let's suppose that we're going to use some of the odds data to actually get the surprise score. What other information do you think we will need if we're wanting to make some kind of score for a player and a year? What other key variables from the data set will we need to focus on? For the player of the year, that stuff, we're going to need the winner-loser information, their names, and then there's some kind of date variable, right? Because we need to know, we have multiple years, we need to be able to say which year it was because we want to give a score for a particular year. So the key variables will be the date, winner. So for this score, we're just going to focus on the results where a player won the match, and then one of the odds, some of the bookmaker information. Okay, so let's see. We're going to use the odds. If we want to summarize by year, that's not actually a variable that's already in the data set. So we'll need to create that. If we're looking at the winner names, we'll also want to check if there's anything funny about the player names. Because if we're looking over multiple years, maybe something has changed in the way that they've been named, or there's some kind of, misspellings or things there. So we'll want to check that. We'll want to actually create this surprise score. How are we even going to measure that? And then, as I mentioned before, in this case, we're going to filter out retirements because we're going to say, okay, that's not really something that we can attribute to the winner's performance. It's more of a measure of some probably injury with their opponent. So we'll just remove those entirely. Okay, so that's bringing together a number of different things. So the first is a date conversion. We have this string. We need to actually get a year value from it. You can do a string manipulation, but because you probably will want to use that date for other things, I would suggest creating a date object and then using some of the tools that come with those. So the main package for that is lubridate. It's a very convenient way to turn characters into date objects where you can do a whole kinds of things of numeric operations on dates in a way that makes sense for a date type of object. So the first thing is doing the conversion, and these are the basic commands that you can use depending on the format that your data comes in. So essentially you need to figure out where's the day, where's the month, where's the year. Once you do that, you need to just use that same order to call the appropriate function. So if I have a date, month, year format, I will use the TM1. If I have a month, date, year, I would use that. And pretty much you don't need to do much else. The lubridate is very smart in sort of looking for the delimiter. You don't really need to specify any of that. The only thing you would need to be aware of is if over your date, if for some reason the format changes at any point, that would be something you'd have to correct. But in this case, we have the same throughout. So if we actually look back, let's see, at our date variable. I'll just exit out of this. Okay, so if we look in our date. Okay, so if I'm going to use lubridate on these, let's see. What is the appropriate function? Right, so we've got, it helps to know that the Australian Open's in January, but you can also just tell by what's a plausible range for each. So once we see a 19, we know that's most likely going to be the day, and then month, and then year. So then I would just load, make sure I have dplyr and lubridate loaded, and then I can combine the mutate with the functions from lubridate to just create, here I'm just actually replacing the original date with its date object version. And then in the next step, once I've done that, it's already available to me to use in its date object form. And then I can use the year function. That's one of the date methods with lubridate. And it'll just extract the year for me. And then we can go ahead and inspect the result just out of interest. Okay, so date's now a date object, and we can use all of the methods from lubridate for that if we're interested. For now, we just needed to get the year. Okay, so the next thing is, how are we actually going to measure surprise? And this is kind of the most fun part in a way, because you get to be creative in how you would evaluate performances and try to come up with an overall score that might be reasonable for identifying kind of a string of upsets. So, but the basic thing is to think, well, when we're surprised about a player's results, is basically when they did much more than was expected of them, and maybe did it repeatedly at a particular event. So how would we go about measuring that? Fortunately, with the bookmaker odds, those are essentially expectations from some kind of group of experts that can help us to establish sort of what did everyone think they were capable of at the start of that match, and then we can compare what they actually did, so their actual wins compared to what was expected, and sum that across all of their matches won in a particular event, and we'll call that a surprise score. And so the higher that value, the more positive that value, the more surprising that player's outcome was, because they were playing over expectation. So here's how I would first look to say, well, which odds are we actually going to use? We saw that there's a whole range of these. You could do something like some kind of consensus measure, but let's say we just want to pick out the one. So one criteria might be, well, I just want to use the one that's most complete, is available for all of the matches, because maybe there's some in there where maybe the bookmaker didn't actually post a price for that match. So what I'm doing here is using the summarize all across all of the odds variables in the data set. And I'm using the shorthand range that dplyr allows, where you can actually just specify using the colon to go from every variable that starts with the B365W and ends with the average L. So having inspected the data, I know that that's going to cover all of the odds variables. And then the summarize all is something where I can apply functions across all of those selected columns. And in this case, I'm just looking, I want to know how many missing variables there are, so wherever there's a value that's missing. So what I've done here is using the isNA, which returns trues and falses, putting that within a sum, and then this dot operator is something I can use with the summarize all to just create kind of an anonymous function, because there's not really anything that gives me the sum of missing, not that I'm aware of anyway, but you guys might know. But this is a fairly straightforward way of just creating a little function to do that. So the result you'll see is just going to be a single number that tells me the total number of missing. So there's not actually too much, but we do see that there are some of these that have one match that they don't have information for. So just to be the most complete, I'm going to then focus on the B365 odds. I don't have any other particular preference beyond just the one that's at least one of the odds that are most complete. So let's suppose we just use that particular set of odds. Now, in a tennis match, actually, one way of converting the odds, sort of a simple approach for getting an overall measure of the expectation, is to just convert them into the win probabilities. And so an approximation for the win probability that's implied by the starting odds by the bookmaker is just to take the reciprocal, given the format that we have them in this data set are these decimal type of odds. So all I'm doing here is I'm taking the winner's odds at the start, I'm taking the reciprocal, and that then puts it into a value that would be roughly what sort of the win probability was. So let's say if a player had a price of 10 or decimal odds of 10, then that would correspond to example for kind of a 10% win expectation that they would actually win that match. okay? So then what we do is I take, in this case, because we're only focusing on the wins, I would take 1 minus that to give me the overall score of surprise, because I'm taking what they actually did, which was they won, so they get a full total of 1 as their probability, and then compare that with what was expected. So that number will be larger the more they performed beyond what was expected at the start of the match. So this is just within a mutate command, and that allows us to then use that for doing any kind of summary. So I've just created a new variable for all of the winner outcomes. So what we're going to want to do is to summarize those surprise scores by player and year, but we haven't yet checked that the names are in the way that we want. So we're going to have to do a little bit closer look at that winner variable. One thing that I think is fairly convenient, there's no real one easy way to deal with all of the issues that can happen with naming problems, just because, you know, there can be misspellings, there can just be variants. But one thing that you can do is to use the agrep, or an approximate grep, which is basically a fuzzy matching function, to look for similar instances of variables, and that should catch most of like the major differences that you would come across. So essentially it uses this Levenstein distance to look for 2 strings that are similar, and you can kind of control that criteria of similarity with the max distance command. So these are the default values and the basic syntax. So I would use it just like I would a grep command or some of the pattern commands that we saw with the stringer package. But it will require that you don't have an exact match, just has to be close enough based on the max distance. And this can be helpful to pick up on things that we might not anticipate ahead of time. So let's see a case of this at work. So I'm going to take the winner vector from our data set, and in this first line, let me just do this in sequence so it's easier to read. Okay, so the first line is just making a vector of all of the unique instances within the winner variable. So that gives me essentially all of the players that won a match at any of the AOs that we're considering. Now here's a step, this approx, where I'm actually using the grep and I'm running through every player and I'm checking them against the whole set of players. So I'm comparing them against all of the other players to say if there's anyone that looks sort of similar among that group. And this will just return a list, so we can look at the first few elements, for example. And what it'll have is a value of every time there was a matching, a fuzzy matched element. So in most cases, if there is just a single match, that means it just matched against itself, and that would indicate that there's nothing peculiar with that. But if you have any instances where there would be multiple matches against, so when I took one player name and looked across all the players, if there were multiple matches, that means either that name is very similar to someone else, maybe, and in some cases it may be valid, but sometimes it might pick up on some peculiarities that you need to address. So this is the actual result when we run it on the winner, and so we get these 4 players picked out, and then what we would do, so these are all the players that have multiple matches on this fuzzy matching, and then what we would do would be to, we might know offhand, just based on our knowledge of the sport, what some of the issues were. Like I know that these are both brothers, so I know that there's nothing wrong with that, that's fine. But with these others, it wouldn't be clear to me exactly why these were picked out. So what I would then do would be to inspect those cases. So for example, when I look to see, well, why was Bautista flagged? And the reason for that is that there's actually 2 variants of his name if we look among the winner variables. So for example, I can look at, now once I see that Bautista Bautista is getting matched, I can then try to understand, why that might be. And here's a way you could use the grep command, for example. And this now shows me, again, it would be something that you'd have to have some knowledge of the sport to know for sure if this could be two separate players, but in this case, it's actually a single player. And there are just multiple ways that his name is sometimes spelled. So this would be one that you would have to clean up, because imagine if you were doing any summaries by player, now it's going to be treated like two different individuals, and it would not be an appropriate representation of that player's, performance measurement. So in this case, after doing that, I would need to do this one correction. This would be one thing I could do to fix up that data type. And all of the other cases that were drawn were actually fine as they were upon inspection. Okay, so now we're ready. We've got everything in place to get this surprise score all together. And so now, like I said, we wanted to summarize this surprise score that we've created by the winners. We've made sure that the winners are identified as they should be. We've created our year variable, so we're going to do the summary of the scores for every year and winner. So that's done with a simple group by. We have our summarized, and I'm just going to take the sum of the surprise score. So the group by already naturally does that within year and player. And then the only other stuff I have at the top is to filter out those retirements, and those are just identified as rows wherever the comment was equal to retired, which we saw when we were doing our inspection. So putting all of that together now gives me an overall score for every player and year, and then I can order that, in this case, if I do the decreasing to true, that'll put the players that had the highest surprise scores at the top of the result. And, okay, I'll have to actually run this one. So let me make sure I have my surprise score in there. We've updated the winner, so let's actually look at what this information gives us. Okay, so we're going to look at the top 10 players that come up. So, for the tennis people, this would be more interesting, but actually a couple of these were from, the first two on top are Misha Zverev and Denis Istomin, the one that we saw in that photo. Those come up as two results that were particularly surprising. And actually, that's pretty consistent with what the commentary suggested. It's pretty cool, too, that even Roger Federer, who ended up winning the AO this year, it was also quite surprising, I guess partly because he had a shortened 2016, and so no one really knew. He's a talented player, but no one kind of knew where he would be at coming back, and everyone thought Murray and Djokovic were going to be doing quite well. So that's kind of, an interesting thing. So you can imagine this would be something, that you might, write up. But the important point was it's a practical example of, like, when I started out, I want the surprise score, but I've got to go through all of these different steps to get there. But most of them I can do with, with tools in dplyr or tidier. And it just gives you an overall, kind of with the practical example, an overall idea of some common steps that you go through with these sort of research tasks. So in this, we did not include losses, so we just focused on wins. If we wanted to incorporate losses, we see that the data, its current structure, would you say, is it a wide or a long format in relation to the win-loser results? I think I heard wide over there. That's correct, because the winner information, the loser information, they're separated by column. Okay? So if we wanted to do some kind of summary where we included both the player's losses and wins, we would have to put our data into a long format to make that more straightforward. So this is where the tidier package comes in, indicates. So remember, our long format is generally stacked. We can think of our data in terms of a key and a value pair, whereas the wide data is generally going to have many more columns. So the basic way to do that is with the gather. In this example, this is just kind of a hypothetical example. I have a data set, let's say, that has x1, 2, 3, and let's suppose that I want to stack those into one variable. I would use a gather to do that. And the first two arguments that you see are just going to say, what are you going to call the column that has the original variable names in it? And then what are you going to call the column that has the values associated with those variables? So I'm just giving them name and value. So that would squish all of these three variables into a single variable. Similarly, if I wanted to break that back down, if I had, let's say, a name and a value type of structure, and I wanted to break those down, then I would use the spread command, and all I have to do here is tell it what is the variable that has the names of the columns I'm going to create. That's the key, and then the value would just be the actual values that go in the rows under those particular columns. Those are the two, essentially the real two reshaping functions that you need. And then in this example, just using our data, applying that same idea, if I wanted to take the winner and loser names and create a single player variable, then I could do that with the gather. And let's say that in this case, I'm going to call the outcome that indicates whether it's the winner or loser as outcome. And then the actual names of those that are contained in those variables will go under player. And then this is just an example of the output that you would get from the betting data that we've been working with. So I'll have links here for some of the major tools in that section. But that covers a lot of the sort of the manipulation and the reshaping tools that you'll use to prepare your data for actual analysis. Okay, so the next section, we're going to talk about doing some data exploration. Now we've actually got our data in shape. We're ready to start looking at it and generating some interesting questions. So this whole kind of exploratory data analysis, a lot of it stems from the work of John Tukey, who kind of established that whole terminology. And I thought this quote was interesting just because it kind of relates the process of doing exploratory analysis with sort of being a detective, and that's often what it feels like. We're really going through and having questions and looking to see, how well they're supported or not by our data. So one of the key things is having some specific questions when you start out. I mean, sometimes you're maybe just interested in, what do these variables contain? What is their distribution? You might have some general questions like that would be part of the process, but generally, with any kind of large data set, you're going to want to have some structure. So in this example, I just wanted to go through a few tenets and myths to make this a little bit more fun with the exploratory data. So in tennis, commentators say a lot, and they're often things that aren't always really checked by data. So I picked out a few things that are kind of common axioms in tennis. So one is that the second serve is more important than the first serve. You often hear the commentators over a match say, the second serve is going to decide this match, and so on. Next, you often hear that players who serve first in a match have an advantage. So during the coin toss, commentators might say something about, that's really going to make a difference for this match because they're able to get served. So it's something that's determined randomly at the beginning of a match. And there's this notion that somehow getting to serve first will give you some kind of edge. And then finally, the seventh game, the all-importance of the seventh game. Often when it gets to 3-all and players are in the seventh game, then commentators will say, the outcome of this game is really going to be important for deciding the match. So these would be things when we start out. If we have a data set that has information about results in tennis, like we get from the Juice package, then we can explore these different ideas to see, maybe with just some initial summarizing, we can get some sense of what, is there any evidence to support these things. So I wanted to, let's take a crack at this first question about the importance of the second serve. And to do this, we're going to use the ATP matches data set from the DEUCE package. And we're just going to focus on the years from 2005 to 2015 to stay within a kind of somewhat consistent time period with respect to how the game has been played. So this is all going to be focusing on the ATP. That would all be men's matches. Okay, so I've used the filtering step from dplyr to just isolate that particular range of years. And the data set already had the year variable in there, so I could just use that directly. And again, like we saw previously, I could go to the manual page to inspect and learn more about the particular variables, or use one of the inspection steps that we saw previously. Okay. So with this question, first you kind of have to think, well, what does that mean, this idea of the second serve being more important than the first? So one way to maybe translate that into something that's a bit more testable is you might say, well, if the second serve is more important, we might expect it to have a stronger relationship with the winner of the match. So it does a better job of identifying the winner compared to the loser of the match. So what this suggests is if we focus on the difference in the service stats for the winner and loser, and we look at differences in the distribution depending on whether it's the first or the second serve, that might give us some indication of, is there evidence that winners distinguish themselves more from the losers based on their second service stats compared to their first. So how would we go about doing that? The first step is when we look at the ATP match data set, it has a series of service stats, but they're kind of not in the format that we want to use. We want to actually have just a percentage value. So we'll use some transformation here with the mutate. And the first serve win percentage can be calculated by taking the first serve one for the corresponding player, in this case the winner at the top row. And then the service points, that just has the total service points. So if I divide, that'll give me the percentage of the service points that were won on the first serve. And then for the second, it'll be the second one with the same denominator. And so I do this for both the winner and loser. I'm creating 4 new variables that just contain the proportion of first and second service points won. So I'll do this in the console in case we want to refer back to it here. Okay, so one of the things I might first do as part of this exploration is to then summarize the difference between these data. So let's have a look. If we run this, it should correspond. So what are some issues that might come up here? What's one thing from this summary that? A lot of NAs, yeah. So it turns out that a lot of these matches from the source, the match stats just aren't available. So this will be something that we either will have to be aware of whenever we apply a function to know how it handles missing data, or we might just want to filter those matches outright. So of course we want to go back and understand, like, is the presence of those missing data maybe introducing any bias? For now, we'll filter those out and just focus on the cases with the NAs. Another thing actually with these data as well is that you sometimes have stats that have 0 values, which is essentially, I think we need to treat those as missing as well, particularly if it's something like a service points. Like every player is going to have service points if that match actually completed. So that would be another thing of like, there's something peculiar about the data that was collected for that match. So all of these would be things that maybe just for an initial kind of exploration, we would want to use as filtering. And then as we saw before, sometimes retirements you might want to treat differently as well when looking at this question about the relationship between performance and outcomes on a typical match, a typical completed match, since retirements are a bit kind of unusual cases. Okay, so all of these could be done with some subsetting, filtering steps. So here what I've done is to just done my summary, but data, if we think back to this idea of the first serve being less important than the second, does these data maybe suggest whether the data would support that conclusion? So remember, we're looking at how winners and losers differ, and the idea was that if a variable, the more that it relates to winning the match, we might expect it to see larger differences between the winner and loser on that performance measure. So just looking over this, it sort of suggests that we're seeing larger differences when we look on the first serve stats compared to the second serve. So another way of saying that is that players distinguish themselves more, winners and losers of matches distinguish themselves more on the first serve than the second, which would suggest maybe that this notion of the importance of the second serve might be a bit problematic. Looking at these values, I mean, it is one way of summarizing, but generally when we're exploring data, we want to chart, because like visualizing the data is going to be much more helpful in identifying interesting patterns. So most of the exploration we'll do is with charting. How many of you use ggplot? Oh, good, okay, so I won't have to say much. And it's nice as well because it kind of is another thing that fits in with this whole kind of tidy versus grammar. But just as a quick summary, so you all probably know ggplot for the grammar of graphics, it does have a kind of unique grammar, particularly when you compare it to other like standard plotting functions in R. So I just kind of organized some of the main parts that go into specifying charts in ggplot. So we've got the aesthetics, which really define which variables correspond to different axes. And then the geoms are really about how stuff is drawn. Are we doing a distributional type of graph? Is it a scatter plot? So the geoms would specify exactly how the points specified in the aesthetics are actually going to be rendered. Faceting is something if we want to do like a multi-paneled or previously sort of the lattice charts is what did this, but the faceting is a way we can create rows and columns of plots. The scales are going to control our axes and how those look, as well as any aesthetic features like colors or sizes. We can do that through the scales commands, how those are actually rendered if we want to modify from the defaults. And then themes are kind of an all-around set of stylistic settings. So if we like the way that a particular theme looks and we just want to use that, we can then incorporate that just through a theme command. So we have these serve differentials. If we wanted to use a chart to present those data, we have to do a few things. We'll have to reshape to put into a long format. So in general, most of the plotting function we'll want to do with data that's in a long format. It will just make some things like grouping by the data, faceting, things like that. It's generally more straightforward. In this case, I think we have essentially a distribution that we want to show. So one of the geoms that is good for that type of data would be a box plot. So we'll use the geom box plot in this example, and then look at the results, and again, think back about our conclusions. So putting a few steps together, again, we have our first filtering step that we did in the summer. Now I'm just applying that to the data set to get it ready for plotting. And then I'm creating a variable that has the first and the second serve. And that's the thing that I want to put into a long format. So as it is, it's separate columns, but I'm going to stack those together using the gather command from tidier. So now I'll have all the differential, the serve stat differential, and then I'll have another column that will tell me whether it's the first or second. And then I can just use that as sort of a categorical variable in the plotting functions to distinguish those. So now that I have my serve stats data set, I load ggplot and ggtheme so that I can use some of the kind of customized themes to make this a bit prettier without too many commands. My aesthetics in this case would be the value that actually has our differentials, and then x is going to be the x-axis, which will basically just separate the box plots by first and second serve. So this is a basic version. I'm not doing too much customization. I just request the default box plot, and then I'm just going to use the GDocs themes, which is one of the GG themes. And this would be the result. So fairly vanilla, but it already kind of confirms what we saw from the summary. So I've got my first and second, and you can see that the values for the first, generally, that distribution generally shifted up more positive, which again means that there's a greater differential between winners and losers on the first serve compared to the second. So with the some other things that you could do, you could modify the themes, we could add coloring and things, which I'm guessing you're all pretty familiar with already. The main point is using the geoms that correspond with some summaries of interest to visualize our data and help in interpreting around the questions of interest. And I think in this case, we would say, we haven't done any formal testing, but just the general properties of the distributions would suggest that there's not really evidence to support, at least from this serve differentials alone, to support this conclusion, this general myth in tennis. Okay, so the second myth that we wanted to look at was this idea of serving first and what advantage it has. In this case, we'll want to use point level data because we need to be able to identify who was serving first. So from the JUICE package, we have Grand Slam point level data in this GS point by point. So all I'm doing here is I'm calling that data. That data frame has data for both the ATP and the WTA and then some juniors data as well. So I just want to focus on the ATP. And so I can do that with this filtering command, another dplyr standard. So with the serve advantage, what do we want to do? We want to basically identify individual matches and identify who was the player that served first and who was the player that served second, and then look at the outcomes of the match based on those two player characteristics, and then chart that information. So what we're going to do is look at our overall measure of advantage by the serve. It's just to look at who won the match. So did serving first, winning the coin toss essentially, did that have any relationship with actually winning the match? So it's a little bit of work with our kind of manipulation tools and being a bit familiar with the data structure. But in this case, we'll just want to sort to make sure that everything's in order in terms of the point number, so that we make sure when we identify the first server that we've done that correctly. So I sort based on match, and then let's see if I can scroll to the right. So I'll bring this up in the console so that we can see the full set of code. So if you look here, the point number is the second ordering variable. And by default, it will go from smallest to larger value. And then I create this serve advantage data frame, which is going to have, so I'm grouping by match, and then within match, I'm identifying the point server. So the point server contains the indicator for the first player, which is going to be a 1 or a 2 value. And then I'm looking at the winner of the final point of the match. So this n parentheses is a dplyr command that goes to, it tells me the value of the last row, and it will be within whatever grouping categories we have. So if I go to that value, it tells me basically who was the player that won the last point, which is the winner of the match. So this tells me whether the first server won, and then I do a similar thing for the second server. So if the point server and the first was player 1, then I know that the player that served second was player 2, and then I can do a similar check to see if that player was the winner of the match. So those are the two basic variables I would need. And then I do a summary across all of the matches to get the overall win percentages in each case. And now I'm ready. I can gather those again like we did before, so that I've got to represent the win percentage for the players that serve first and the players that serve second. I've done a little bit more customizing in this one, so I've modified the label of the scale to the scale y continuous, because we have a continuous variable for our y-axis. And then I set the limits to make sure that it shows all the way up to 100. I know the percentages has to be from 0 to 100, so I want the full range represented. And then I've added a fill character, so the first, second serve order will be a categorical variable, and I can specify that as an aesthetic so that the bar will change colors depending on whether it's the first or second. And then this fill command here just has to use this Tableau palette for that fill variable. And then again, I'm using the gdocs theme. And in the end, you'll get something like this. And now we're ready to actually interpret. So we see the percentage for the first serve 1, second serve 1, is quite large, actually, about 10 percentage points. So in this case, if we think back about this myth about the advantage of the first serve, what would this chart suggest? There's something probably to it, actually, which is kind of surprising because it's just, a coin toss. And you can imagine things like, well, they have fresh balls at that point. Maybe there's something to that, or maybe there's something psychological about getting, that maybe the players have bought into it and then they have extra confidence just by winning the coin toss. Hard to say, but at least this one, it looks like maybe there's something to that. Okay, and then finally, I have an example here also we can look at that game 7. It's using the same data source and some similar kind of manipulation. In this case, we're looking to see the relationship between the winner of the 7th game and winning the set. So this is more of like a set level phenomenon than the match. But you could do a similar thing, and then I think the only thing here is you might want to only limit it to games that were sort of close, because that's when I think commentators are kind of more interested in cases where you have two somewhat equal opponents, so probably eliminate games that were kind of very lopsided. So that filtering step does that. And then otherwise, we do a similar thing, summarize the overall percentage of set 1 by the winner of game 7, and then we're ready to plot those data in a similar way. And in this case, we actually see more of an advantage for the game 7 loser. So, but it may be that statistically there's actually no difference between those. So we've gone through some kind of exploratory data to look at 3 different myths in tennis, and we've seen some evidence to maybe support one of the 3, and looked at how we can use these kind of combination of data manipulation and charting to get at these types of questions before we're ready to do any sort of modeling. So basically, your key tools are still going to come from dplyr, and most of the exploration you can do these days are available through the ggplot package. So some more kind of advanced, once we're at the point where maybe we're interested in doing some real analysis, one of the common ones in sport is predictive modeling. So once we're at the point where we're actually wanting to do some estimation, a very common one in sport is forecasting, because everyone wants to know who's going to win or what are the things that are related to winning. So I wanted to point out some tools for predictive modeling. The first thing, though, is understanding the difference between when you would want to go to those tools versus do something that's more descriptive in nature. So prediction is really when we're just focused on getting the best forecasts possible. If we're more interested in understanding the association between variables, or how maybe one performance metric is related to an outcome in an event, so something maybe that's closer to kind of the causal inference or association analysis, that's going to be more descriptive in nature, and we might want to use something like a regression type of approach for that. For predictive modeling, we'll generally want to use more machine learning type of tools, which have, in most cases, shown to outperform descriptive modeling-based approaches for forecasting. But But I do think before you do start doing any kind of machine learning, because it's sometimes complex to really evaluate what's happening underneath those tools, I think it's good to do some descriptive modeling before, just almost to kind of ground what your expectations are related to certain explanatory variables, and also sometimes the descriptive modeling can pick out peculiarities that you might have missed during your EDA. But those would always be like first steps before, and often, you know, that's going to come from something like a GLM type of model. Okay, so once we're ready we know that we have a problem, we're interested in prediction, and we're ready to apply some of those techniques. I think one package that's very useful for this in R is called Carrot, and this is written by Max Kuhn, and there's actually an accompanying book that describes this. There's a Springer applied predictive modeling, but he also has an online book that has a lot of the content that you will need as well, and there are links to that in this section of slides. So that package contains over 100 different types of machine learning techniques, and the important thing is it has a sort of streamlined approach for how you would set up your training and model development and evaluation. So you can use all these different methods, but you kind of have a nice sort of uniform way of going about doing the development. So I want to just walk through that fairly quickly so you get some familiarity if this is new to you, and also show you kind of the basic functions that you'll need with the Carrot package to apply different methods that you're interested in. So the first is deciding how to spend your data. Generally going to split up our data into training and testing data sets, and so we need to decide how exactly we're going to do that in terms of the proportions to allocate and how we're going to sample among each data type. Then we'll actually do the splitting. There may be some pre-processing that we'll want to do to the data before we prep for modeling, just to make sure that we avoid any kind of peculiarities due to having like non-standardized data. And then then we're ready for the actual training. And then the final step would be, once we've trained our data, we'll evaluate the metrics both within the training samples and against our test data. So with the splitting, essentially this is a safeguard against overfitting, or what you can think of as kind of like the machine learning equivalent of Monday morning quarterbacking. It's like if you've seen that data before, you're generally in a better position to kind of know how it behaves, but it doesn't really give you a realistic idea of how it would perform if it sees entirely new data. So that's the whole purpose of using this test data set, because it's supposed to reflect more of like a real life example of how that modeling tool would be used. The way that we do that in Carrot is with this create data partition function, and all you really do is you just give it an outcome vector, and then you make some specifications on how you want it to be split. So with the times argument, I could actually ask for multiple splits if I want to create my own resamples. And then P would just be the actual proportion that I want allocated to training. And there's no single rule about this. I mean, often it's kind of a balance between the precision in your training estimates and then your ability to like accurately evaluate performance in your test data. But a general standard is to use about 70% for training, so you generally allocate more for training. So here's an example of what this would look like. Let's suppose I have a data set. Data, my outcome vector is called outcome. I would give that to y, the y argument. And then the times, in this case I'm just asking for a single partition. And I want 70% of my data allocated to training. And so what this will return is a vector that will have an index location of the rows for all of the data that was sampled to go into my training set. So then I can use that for splitting up the training and test data. If I wanted to take that previous example, and let's say now I want actually 5 resamples, and I want to just have 60% allocated, this would just be the way I would modify that argument call. And in this case, it will return a matrix, and each column will be a different set of indices for the training data. So once we have sort of our information for splitting in place, before we split, we will want to do any pre-processing to make sure that it's applied both to our test and training data. And generally, this pre-processing phase is just about dealing with anything where you might have variables that have very different distributions in your feature set or your possible explanatory variables. And that's mostly a protection, particularly if you're going to be using any like regression-based methods. They're more sensitive to unstandardized variables. But it's generally a good thing to do if you're going to use the data interpreting the results. Sometimes that can be difficult. You can get some misleading results if your variables are on different scales as well. Looking for highly correlated variables also can be important, because another way of thinking of that is just that those variables provide very similar information, so they're not really adding any value to the information. So it might be good to do kind of a scan for highly correlated variables before. There's also methods for doing this automatically through dimension reduction, like a principal component analysis, for example. If you have that's more, I think, of something that's very important when you have many, many variables. So if your number of explanatory variables is sort of approaching or even exceeding your sample size, then you'll definitely will need to use that. So those would be things that all would be kind of within this pre-processing step. Once our feature set is in order, the basic thing for starting to develop our models are with this train function in caret. And so the key elements of it, we have a formula which we would use in the same way that we would a descriptive model, except that it's really just telling it which features to look at. We could do some transformations and things at that point, but generally it's just something to distinguish our outcome variable from our feature set. The data set that stores those variables, and then the actual method that we're going to want to apply. So this will be the type of machine learning approach. And the actual name we can get from, there's a get model info, for example, or from the online documentation would contain that as well. We will want to specify metrics. So one of the things is there's some summaries that will come out of the training data. And if you have multiple resamples, which is good practice to do, or let's say there's different tuning parameter settings that you'll see that we can control with some of the tuning. That means that there are going to be sort of multiple instances of the models that you train. And when you want to look at sort of which is performing the best, it's easiest to do that if you have just a single metric that you focus on. So you can always look at multiple metrics like when you're doing your evaluation afterwards, but just in terms of a way of summarizing the overall performance and what appears to be more optimal, you'll want to just specify a metric for that. And we'll look at some of the common metrics that are used depending on the type of outcome that you're working with. I mentioned tuning. So each model will generally have a set of parameters that are basically kind of control variables of how that model is implemented. So they'll be specific to the model, and again, that there are functions in caret, the get model info, which will point out what those are. If you're just getting started and you want caret to sort of pick a reasonable range for you, then you can use the tune length argument, and essentially you can just give it a number, and that'll be the range over a set of different values over a well-selected grid that it will try to get some variable range of the parameters so that you can see if it's making any sort of difference in the performance. Okay, and then we have the train control argument, where we would specify some things about how the resampling is done among the training, as well as any changes to the summary performance metrics that we might want to make. And then finally, if we want to actually control the grid parameters directly, so if we get more familiar with the method, or let's say we find a range that is looking better and we just want to explore more finely within that range, we could do that within a tune grid. So this would basically be in place of using the tune length, and you would just give a data frame that would have a range of the values that you want it to evaluate the model at for the tuning parameter parameters for that method. Okay, so I'm going to skip. You guys probably know if you want to standardize your variables, you could use the scale function. Okay, so I mentioned the train control. One of the key parts of it is resampling. It's essentially having multiple samples within your training data. And again, it's another control against overfitting. And part of the reason why this is really important is because in practice we know that we'll evaluate on test data, but we'll still probably go back and do more modeling. So in a way, you know, the test results is still kind of influencing, even though we've separated the data, there's still potential there that we could be misled by all of the modeling repetition that we're doing. So one way to help against that is to make sure that you have some sort of cross-validation, bootstrapping, and multiple samples that you're testing over. So one way that you can do that with the train control function, this is a way of specifying the control settings that will go into the training function. So in this example, I'm using a repeated cross-validation with 5 different repetitions. I'm also asking, in this case, I'm supposing I have a binary outcome, so sort of I can treat them as zeros and ones. And if I want to modify the performance metric from the default, which I think is like an overall accuracy, then I can do that by specifying the 2-class summary, which just makes the model's estimated probabilities for those classes available, and then I can apply different performance metrics to that. So I'm storing the result of this train control object into control specs, and then I would give that in as the train control command in the train function. I mentioned before, another thing you might want to specify is this tune grid. And a common way to set that up is just by using an expand grid, so you can give a range of values, particularly if there are multiple parameters. That's not a caret function, it's just a standard part of the base R. Okay, but the key thing is using this get model info. So let me show you exactly what that does. So if I just said get model info after I've loaded caret and just had blank parentheses, it would return all of the hundreds of models as a list, and in each list it would give me information about the specifications for that particular method. If I already have an idea of what model I'm interested in, so in this case I'm looking at an R-part type of cart model, I could just give that model name, and then I'll have a list object that'll just be specific to that particular model type. So this is kind of the content that you would get. And the key one is in this parameters, this tells me where the tuning parameters are for that particular method. So for this case, you've got a CP, or the complexity parameter. So it's just got a single parameter that you would tune. So if I wanted to then create a grid for that, I would create a data frame. It would have a CP value, and then I would give the range of values for that. And for any of these, because it's taking from all sorts of packages to provide these different range of methods, you could always look back at that the source for that original method, which would also be information, so this tells me as well, this comes from the R-part package. So I could read there if I wanted to know all of the details about how this is working. Okay, the last bit is the metrics. So for the most part, we're often doing classification with machine learning, and these are going to be some of the basic measures that you use to actually say, like, how good is this model performing? The most basic one is accuracy, so it's just like, how often is it getting the class correct? But it's a bit crude in the sense that you don't know with what sort of confidence it's making those. So the log loss is somewhat of a preferable method in the sense that it says, well, you might be wrong, but you could be wrong by a small percentage. In other cases, you might be way off, right? Your prediction of that class might have been 90% or higher. So the log loss will take that into account. So you can almost think of it as kind of like a weighted accuracy measure. And then you have some other ROC-related type of measures that are all available to use with the caret package as well. If you can do regression type or like a continuous outcome, and they're generally an R squared or a root mean squared error would kind of be the typical performance metrics you would use there. If I wanted to use the log loss, I would change my train control here and ask for the MN log loss, and then that would allow me to use the log loss metric in my train call. This is just an example. You can do other types of sampling rather than like the multi-fold. You could do a type of bootstrap. You can look at the train control to see other specifications there for different sampling methods. Okay, so now we're ready. We've got all the basics to actually implement some training. Like I said, there's many models, but these are some basic classes that are available. You have like forest type methods, boosting, and a whole range of like support vector machine. There's also like neural net type of models available. And they all, sort of have different advantages. But it's generally good to make sure that you look over something from a few different categories, distinct categories of models, because it's sometimes hard to know ahead of time of where you might see better performance just based on the nature of your data alone. Let's suppose that we wanted to do a random forest, just to actually give an example of the training. So this is how I would specify the training setup. So I've got my training data, which I can create a separate partition from my original data source through that train index created with the create data partition. So once I've separated that out, I just need to specify that I want the RF method, which is the correct name for the random forest method. I'm just going to ask for caret to go ahead and pick a range over whatever tuning parameters there are for the random forest of using 10 values across any of those parameters. The control specs I had set up in the previous slide, and here I had set them up so that I could use the log loss function as my performance metric, just when evaluating the different results across the tuning parameters. If I wanted to be more precise on the tuning, like I said, I can look back. You can use the get model info, and I can see that, oh, this M trie, which corresponds to how many predictors any particular forest set of models will look through, like what's sort of the maximum that they'll choose among. I could set, that's the only tuning parameter here. So if I said I wanted to limit it based on the size of my data set, just to be within 5 and 25, just take a selection of values of 10 among that, this is how I would set the data frame. So you need to actually put a dot in front of the tuning parameter variable across all of the methods, but otherwise it follows the same name. And then I would store that as this object called grid, and I would give that under the tune grid argument in place of the tune length. So then I know exactly what I expect the different settings to be in my trained model. Once I get the model, I can apply, there's a plot function, print to see the results. And that would be the main ways that you would evaluate the model. The optimal model, which is going to be selected based on the performance metrics, so the log loss in this case, will be chosen based on that log loss measure, and it will be available as this object called final model from my training. And one thing to keep in mind is you can use all of the methods. That will be the same object as whatever the source package, so the random forest type of object. So I can apply all of the methods that go along with that object to it. So for example, one of the methods the random forest has is this importance measure where you can sort of evaluate the relative importance of the features. So I could use that to the results of the final model of caret as well, just like I would if I had just fit it directly from that package itself. And that could be another way to help with evaluating for those methods that you've already used and been familiar with. So a bit of a crash course. I know we don't have enough time to go into a lot of these in detail, but hopefully if this is a new package, you can see some of the convenience it has in terms of if I wanted to try out a separate model, all I really have to do is really change the method name and and maybe something about the tuning parameters, but in general, you'll probably use the same sort of sampling settings and performance evaluation. And there's even some tools in it to, if you make sure that you reset the seeds each time you run a new method, you can then actually do direct comparisons across them with this resamples function. And that can help to just say, based on my training data alone, which appears to maybe be performing better than others. Okay, so finally, for those of you who might be interested in doing some sports writing, I wanted to mention how you can create blogs by just really knowing a bit about our Markdown. Okay, so blogging. Blogging makes us happy. No, it's a really great way to share the things that you're thinking about, without. It's good also to do academic papers, but we all know that that's a very long, time-consuming process, and you're pretty constrained in how creative you can be in terms of the writing. So this is a fun way to get things out there quickly and just share your interest in sport with other people. This is a clip from my site. It's actually generated from Blogdown, which I'm going to go over, yeah, it's all tennis, so you might not be interested in it if you don't follow tennis, but I just want to show you that creating, a fairly nice-looking site like this is really something. You could do this in a day, and the thing is you just want to focus on content, because that's the hard part of all of this, right? Is having interesting things to say and share with people. And the nice thing about these tools is that you really don't have to know too much about HTML to already get a nice functioning site with a lot of features. So that just allows you to have more time to just think about what you actually want to share. So how does this work? There's actually a package that's been created, Blogdown, that allows you, really just knowing our Markdown, or even if you're already familiar with Markdown, that you can start creating a site. So here's the basic steps. So what you would do is basically create new content with your Markdown, and then you would set up the site with the Blogdown tools. So there'll be a series of functions, and all you really need to do is set up the Hugo code. So install Hugo, and this is just a static HTML site generator. And then you'll just have to give some thought about how, when you're at the point where you're ready to actually deploy it, how you want to go about doing that, because there's a number of different options. For most of us probably who are familiar with GitHub, that's probably going to be the best option to use. So this package is authored by useR, who's also the author of useR, a number of other packages that tested, and many good things in R. Here are the basic functions in Blogdown. So once you've installed it, there's commands to directly install Hugo through the console. You could also install Hugo directly from the web, but there's a kind of a convenience function. You can add new themes, so that would basically control the particular layout that you would use. So there's a whole gallery of themes that people have provided that fit within the Hugo framework that you can look through and then install whichever you would like for your site through the install themes command. You would set up a new site with a new site command. Actually do site building once you've created new content through build site, and then adding new pages through the new content command. And there's also some functions that would allow you to actually run Hugo commands from the R console. But for the most part, it'll primarily, once you've set up your site initially, you'll primarily just be creating new content and rebuilding the site through there. There is a book basically describing Blogdown that you can get, and this one's written by useR and Amber Thomas. And some parts of it seem like they're still working on, but I think most of the content in terms of getting set up and doing the basic prep for setting up your site, and also some instructions about different options for deployment would all be there. But here's the basic workflow. So you'd install Blogdown, and then you could use the install Hugo to get Hugo installed. You would just do that one time. So you do that once. Then you would find a place where you want the folders associated with your site, identify where you want that to go, and then you would use the new site command with that path name. And that would establish a set of initial sort of templates and an example page at that location, which would be the starting point to modifying the content for your particular site. If you are going to be using like a GitHub option for deployment, or some of the other deployment methods are built off of GitHub as well, so like netlify, and so it's generally a good idea to go ahead and set up a repository there. So at that point, you could start the version control from your site. Then you'll want to probably browse the themes section, as I mentioned, to see what kind of layout you want to use, because by default, there'll just be the one option with the starting site. So if you want to modify that, you'll have to identify the theme and then use the install theme, and generally it'll just be giving it information about the GitHub repo that is associated with that particular theme. There'll be some modification that you'll have to do to the configuration. So you will want to change, like the author content, title, things like this, some of the basic content that goes in the sort of main index page for your site. You would modify that through the configuration file. And at that point, it would just be about creating new posts, which you can do either through the new content or new post. And that's where you just have individual R Markdown files, and they could be actually like Markdown that you would use in RStudio, where you could have R content inside that would be generated at the time that you build your page. That would all happen through that function. So the actual writing of the content would be very much like what you would do just in your standard RStudio scripts. Okay, one thing that I do think is kind of nice to add to these sites when it is something that's on the web are interactive graphics. And there are different ways to do this in R, but I think one that's pretty nice is Plotly, because basically there's this command through Plotly is an overall service on the web for creating web graphics and sharing them with other people. There's also a corresponding R package, Plotly, that allows you to take any ggplot object and send that to Plotly, and it'll render like a corresponding graphic that's an interactive version of that plot. So you really just need to know ggplot and like one Plotly, publish command to be able to create the web graphic. So it's really cool. Like this is an example I was looking at, like changes in ELO rankings among women's tennis players this year, and it had like a scrolling feature on the right-hand side so that I could include, more players. You could do things like select an individual player just to highlight their line to, make it sort of less cluttered. So all of those kinds of things are really nice that you can do with these interactive graphics that aren't possible with a static graphic. So let me walk through kind of the basics of using the Plotly. So once you've installed it, you'll have to create an account on Plotly, and it's free to do, and they'll give you some information. You'll establish your username, and then you'll have an API key. You'll need to give that information at the start of your session whenever you're going to be using, whenever you'll be sending information to Plotly, so it knows to send it to the appropriate account. So you'll just do that by setting some environmental variables. So anything here would be where I would actually insert my username, my API. In here, you would just create your plots in ggplot as usual. And then once you have those objects, you could just assign it to an object. So here, let's say, for example, I've called my plot that I want to now put on the web, gg1. And then at that point, all I would do is say plotly_post, and that will then send that plot with whatever file name I give it to my Plotly account. And from that point on, I can make any additional modification that I might want based on how it should be rendered on the website. So here's an example of I went to Plotly, what a typical chart that I'm editing might look like. So this was one I was looking at serve performance trends for 4 players who were kind of favorites for the French Open. And you can see that there's the data grid, and then information about the layout, the style, could all be modified then at that point before you actually put it on your page. There are different options for embedding. I think a nice one is just to use the iframe of your plot. So you would go to the share bar down here, and that will open up a page that will have information about embedding. So I would just copy this and I would put it in my Markdown file, and that would make that plot available on the website as I see it within Plotly itself. So very simple. It's just, you know, as long as you're already familiar with ggplot, it's just a little additional step to getting that on the web. So that wraps up the tutorial. I know it's a bit rushed at the end, but I will speak with the organizers to get you guys all the PDFs. So hopefully there's things you can go back to and maybe practice more directly. And you know, definitely feel free to contact me if you have questions that come up or suggestions for improving the tutorial. And if you have things that you just like to ask me about sports statistics in general, careers in sports, things like that, I'm happy to talk during the lunch break. And I hope you've enjoyed this, and I hope you enjoy the rest of the conference. So thank you all for attending.